how are you, everybody who is watching this video? I would like to take this opportunity to welcome everybody who is watching this practical or workshop programs or workshop presentation. My name is Olenjolain. I'm very happy to have you today. And I would like to take this opportunity to welcome all the students who are online, and even also I have some physical students who are in this workshop. So I would like to tell you that this might be a good moment for you, especially at the beginner or intermediate students, to take some practical skills. If you do remember that we've been learning about designing the audio amplifier, and then we come up with the 4-block diagram, with mainly 4-block diagram. One for the power supply unit, the other one for the input unit, and the other one is for the control unit, and the other one for the output unit. Then in the next workshop, or in the previous workshop, we open each block diagram. And then we took a focus to actually design a linear power supply. So the title of this workshop, which is workshop number 6, is actual number 5 or number 6, wherever that the issue of numbering is not a great deal, but the actual, it's next after the simulations workshop. So the objective of this workshop is actual to realize what we've been designing on paper, and also what we've been simulating by using different simulation software. But for us, we have just used the Proteus in order to simulate what we've been learning, to see the imitations of what are we going to learn. So so if that's the moment, so I would like to take you that, I would like just to tell you that it could be well if you could have these electronics components and have your setup. Then when you follow the instructions that I'm going to teach you practically with evidence or with demonstration, also yourself, you can go through this practical even if you are yourself or you are alone. So it's not limited that you should have a teacher or supervisor just to supervise you. If you just love electronics and you just love telecommunication engineering or electronics engineering, this is the moment for you to improve or to realize your love. So if that's the case, I would like to tell you that get prepared, have a fresh mind, and then open your mind, open your mindset. And I want to tell you one thing. I usually tell my students since I began to teach more than 14 years ago up to this time, and even if that I'll teach for 50 years or whatever the case, or even beyond my life, I used to tell always people, I don't know everything. So when I'm doing this presentation, don't have a mindset in your mind that I just know everything. But what I have a responsibility to teach others about what I know. So this is the small portion. Possibly even the students or the people who are watching this video they might know a lot more than what I'm going to present to them. So that's how the world it is, because it depends how you invest in terms of the knowledge. So if that's the case, but in case you have a question, don't hesitate to ask. I'll be actual designing or building, and you'll be doing the measurements step to step, one point to another point. And then when I finish one point, I can give you a chance to ask you questions until we finish the overall schematic circuit diagrams of linear power supply. Then we can do the measurements again when the circuit is complete. So if that's the case, let me just appreciate and acknowledge the students or the engineering students who are in this class, who have told me that they have a real love with electronics and telecommunication engineering. But for myself, I told them, and I would like even to tell you who is watching this content online, I don't know if you really love or you don't love. So the issue is, let us do the business. Then after time, it will be known who love it and who dislike it. Okay? Good afternoon, student. Good afternoon, student. Are you ready for this practical? Okay, so let us go to the business. Stop. Okay, so I believe that every student can see what we are going to do. As I said in just a short intro, we are going to implement, or we are going to build a linear power supply of fixed positive voltage. So what are the tools? What are the components and materials that we are going to use? The first thing, the first thing that we need, usually we used to draw these schematic circuit diagrams on paper. So today, instead of having a paper, this is our paper, which is called a breadboard. And the breadboard, it has internal configuration. Students, I say, please attention. Shadrach. Okay, fine. So this is the workbench, which you call the hardware workbench that we are going to use today in this practical. So it's called the technical name is called the breadboard. And there is no any level that you could say that you will never interact with a breadboard as long you want to be a practical electronics and telecommunication engineer. So this is one. Then the second thing that will be tapping the power source. And we'll be using this one is called the power cable. It's not an adapter. This is called the technical name is called the power cable. It's called the what? So we'll be using this power cable in order to tap the domestic power and connect with the transformer. So I'll be presenting the material that we're going to use systematically from left-hand side to the right-hand side as how we have drawn the block diagrams and also how we used to draw the schematic circuit diagrams in electronics and telecommunication engineering field or even in computer field. Then the third component, electrical device that we are going to use is the step-down transformer. So this is the step-down transformer we are going to use, and I will be explaining to you how are we going to use. Then next, we are going to use general purpose diode, which the IC number is 1N0007. So you may order it and even you may find. So we are going to use them in order to build the next block or the second block, which is rectifier unit, right? So these are the diodes. So if, for example, you want to visualize, these are the diodes and they have a particular configuration. Then the next components that we are going to have in this design, we are going to have also a filter unit, or according to the block diagrams, we have also a filter unit. According to our design, we did our calculations according to the choice of the transformer that we have made. And then after doing the calculations, then we used the concept of the ripple factor. We did our derivations, and finally we come up that the electrolytic capacitor that we have to use should have a capacitance of 4,860 microfarad. So in our department, we don't have it. So you are going to use another alternative capacitor with another alternative value. Are we together? So this is called the electrolytic capacitor. When I've been teaching you in theory, we have just focused about the capacitance of the capacitor. But a capacitor has a lot more than what you could have thinking or what you have discussed. I ask all the students who were in this class to look on the screen and to listen. Because when I visit you in your tables or in your bench, I will never listen any excuse. Okay, so this is the electrolytic capacitor that you are going to use. Again, we'll be needing, we'll need to implement the regulator unit. To implement the regulator units, we just need 3 components. The first one, we need a voltage regulator, which is this one. It has 3 terminals, and this also it has the meaning, and the meaning for this hole. This hole is not there for the fashion. It has a particular task. And then these are the 3 terminals which I have taught you theoretically, and you have seen them in simulation. So in simulation, you could remember the schematic symbol of the regulator is not look like this one. Okay? And then we need again to have ceramic capacitors. So we'll be using, in the regulator unit, we need 3 components, as I say. We need also 2 ceramic capacitors. So these are the ceramic capacitors. So we'll need this one, and also we need this one. They have the same, closely the same value. There's no any effect. Yeah. Okay? Then another block which we have discussed is load. Another block is load. So for the case of the load, when we've been learning in simulation especially, or even in theoretical, we say that we are going just to have a light emitting diode. So we are going to have a light emitting diode as the load, but just it is representing. But I told you that whenever you're designing either a DC power supply or linear power supply or switched mode power supply, we always need something we call it power indicator. And in order to indicate whether there is a flow of power, then from that moment you could have what? You could have the assurance that my power system is working effectively. Are we together? And mostly are going to use a limiting current resistor. This one is the limiting current resistance. It has 4 bands of color. And also we are going to use different types of light emitting diode. For instance, this is the red light emitting diode. This is the white light emitting diode. This is the green light emitting diode. This is the yellow light emitting diode. So regardless, there's also a hidden secret in light emitting diode. The goodness of electronics, you might spend even 2 weeks to learn one component and master it and know what is going on. Because, for instance, these 3 components for you as a beginner, you might, okay, usually you should say that all of them are light emitting diode, but they have a difference and it is more technical more than what you're thinking. So it means that, for instance, I can have a class with you, a workshop with you, just dealing with the light emitting diode, and we can spend even 2 hours. And we could not even cover what has been hidden here. Okay? Yes, because there is something which is hidden here. Maybe another day we can discuss. So those are the components that we are going to use in this practical. And the actual, I have listed these components according to what we had in the schematic circuit diagram. But another thing, we say that engineering is all about numbers. Engineering is all about formula. Engineering is all about diagrams. Engineering is all about tables. And engineering is all about graphs. Are we together? So we'll be having 2 parts of this practical. The first part, we say that, or I told you in the theoretical context, when we say engineering is all about numbers, we used to get numbers in engineering by doing measurements. So if you are poor in doing measurements in electronics and telecommunication engineering, I want to tell you that you will be a political engineer. Are we together? So for the purpose of measurements, that's what he said that we are going to do, we are going to have a 2 setup. So for the first setup, we are going to use a digital multimeter in order to do measurements. And for the second setup, then we realize all the 5 parameters or 5 5 terms that summarize all about engineering. So now I wonder, in the class, students are slumbering. Stop. Okay, so I say that we are going to use this digital multimeter for the measurement. And I told you, and I would like to tell you that in most learning institutions, colleges, and universities, there are modules which are called the measurements. In some of the institutions, they call it instrumentation. In some of the institutions, they call it the measurements and the instrumentation. I don't know a lot about what's going on, but I think because you're in this industry, you will go to those institutions and you will learn those modules, and then really assess yourself if really you know the measurements or you know the instrument you have been learning. But for me, frankly speaking, I don't want to hide to you. There is a great electronics and telecommunication secret which has been hidden in this digital multimeter. Amedeo, what's your neighbor doing? So say that, be patient, sir. Be patient with, and maybe keep being patient. So, in order to use this multimeter, this actual, within it, it contains a number of more than 11 measuring and the testing instrument. So to use it, we'll need these 2 probes. We call them probes, or we call them leads. So you have 2 leads. This is the positive lead, and this is the negative lead. In other words, this is the positive lead, and this is the groundy lead. And this is the color code used worldwide. So I think that I have presented to you about the materials and the instrument and the components that we need for this practical. So then we are going to begin our business. The transformers are always built in this form. We have small size transformers, and also we have a large size transformer. So let us start our business with the first block. I believe that you are concentrating and you are focusing. This is the step-down transformer. It does not mean that this is the largest one. This is just the medium. We have the smallest step-down transformer. Within this transformer, you can build the smallest that has been used to design the mobile adapter. For instance, you know they are small in size. So within this one, you can build even 4 other small step-down transformers. So I'm talking about the size. But also we have step-down transformers of almost 5 ampere. Its size, you might find that it's 4 times the size of this one. Stop. Okay. So I told you that we have 2 types of step-down transformer. We have a center tapped step-down transformer, and we have also non-center center tapped step-down transformer. So I told you the difference is actually the number of wires that you have to examine them at the output part. Because when you draw, within it there's a primary coil and secondary coil. And I told you in the class, in the theoretical, whenever you have a transformer, whether you hold in this way, or you hold in this way, or you hold in this way, or you hold in this way, the input is always those wires which are at the bottom of the step-down transformer. So if you remember what I told you, or if you forgot, I remind you. So the input of this step-down transformer are these 2 wires. These are the inputs. Here, this is a primary coil. This is a secondary coil. Are we together? Are we together? So whether it is center tapped step-down transformer or non-center tapped step-down transformer, at the input, they have 2 wires. Are we together? Yes. So the difference is there at output where the secondary coil. So this one, it can be either connected with live wire, or this one can be connected with live wire. In case of alternating currents, alternating voltage, there's no any issue of polarity. Right? So don't claim in your mindset that if just, for example, I light the transformer in this way, this should be connected with live, this should be connected with neutral. That's not true. So don't bother yourself about it, which one is live, which one is not live. And that's why we have a color code of red. Red, in case of high electrical, or in case of electrical engineering, the color code of red means positive. Are we together? So we are in the secondary part right now because we did some maneuvering, some calculations, and we realized those calculations. So on this secondary part, we have 3 wires. I told you that in case you have 3 wires, that is center what? Eh? If you have 2 wires, and those the wires of the secondary coil will be always at the top of the transformer. I'm teaching you this concept clearly and in detail because if you do a mistake and revise what I'm teaching you, you are going to burst it, to burn this transformer. And the practical will end there. Are we together? So if you revise to say that this is the input and this is the output, at the moment you just turn on the switch, then the transformer, sometimes it depends to them, maybe the amount of the, maybe the flow or the variations of alternating voltage. It can burn, actually you can see some kinds of the smoke, or sometimes you don't see it, but the step-down transformer is no longer working. And sometimes, if, for example, you do the electric shock, or you burn it, or you destroy it, then you can find even the wires, they will cut. Are we together? Are we together? Okay. Is there any question about step-down transformer that you have seen? So this is the center tapped, nothing new. I told you that here it means that if we measure the voltage across these 2 wires, this one and the middle wire, I will have a particular voltage. And I told you that in step-down transformer, always there are specifications which have been written. So this is specification when they are being written. Sometimes I taught you in the class, if this is a step-down transformer, that if you measure the output voltage between this wire and this wire is 12 volt. So you might find that it has been written 12 volt times 2. We discussed in the class, if you do remember what I told you. If you don't remember, you have to go through what we've discussed. Okay? So the difference, actually, that means we can measure the root mean square output voltage by using these 2 wires, or you can measure the root mean square voltage by using these 2 wires, or you can measure the root mean square output voltage by using these 2 wires. This blue color and black color have the meaning in engineering. This, we call them color code in wire. Are we together? Are we together? Okay, so that is clear. So then I want now to connect the step-down transformer. When we read the specification, possibly you don't see it has been written transformer type hiyo that ones is 12 voltage ampere. The input is 220, and then the output is 60 volt dash 0 dash 60 volt. My God, my God, my God. Class, are you happy? Okay, let us keep on. So with this step down transformer, hey, keep quiet. Okay, so here you see output is written 60 volt dash 0 dash 60 volt. In the exam, I also gave you a question like that. 60 volt dash 0 dash 60 volt. Or 24 volt dash 0 dash 24 volt. You saw that I have tricked you. It's not a trick, it's a reality. Are we together? I didn't design this step down transformer. This is the departmental resources. Okay. So if it has been written 60 volt, 0, 60 volt, what does it mean? Center tapped. Okay, that's the one of the information. The second piece of information? Output. What the output voltage that the manufacturer declared that you might get from this transformer? 12 volt. Eh? 6 oranges or 6 what? 60 volt. Sita is looking that side. Yes, those are the students that have been given. Mickey Daddy, he doesn't care. It's actual that parallel with what I'm teaching. Okay, so we're expecting to get the root mean square voltage, output voltage of 60 volt and 12. The manufacturer did not say that 60.23. He just wrote 60 volt. And that's why theoretically we wrote that the output of the transformer is 12 volt. It does not have any decimal point. Are we together? Okay. So then we take our power cable. So you're going to connect this one to the socket. So you've connected to the socket. So if you have connected to the socket, then it comes, let me just instruct you because you have to do measurements. If you do remember, in our table of result, we say that the input root mean square voltage is 220 volt. Do you remember that? So today we are in workshop and you have to do measurements. Okay? So if you have to do measurements, this is the digital multimeter. I say that contains more than 11 measuring and testing instruments. And this is another module. For me, if really that I want to teach a student for 15 weeks, this should be a module itself. Oscilloscope should be a module of the 3 semesters. Function generator should be a module of 1 semester. That's according to me. Not according to you and according to what it has been done. Why? There's a hidden story there. And if you never discover a hidden story, you'll never see what's going on. You'll be just doing the usual business, and then life goes, and one day that you say, bye-bye, bye-bye, I'm leaving, I'm going to die. And then you say, okay, best wishes, we are coming also. Okay, so in this digital multimeter, this is off point, this is the pointer. So I'm rotating the rotary switch in order to choose a C voltimeter. I told you in theory, a C voltimeter measures the root mean square voltage. It does not measure the average voltage. It does not measure the maximum voltage. It does not measure peak-to-peak voltage, if you do remember. Right? So before I go to the next year, I feed the AC source into the 4 or 5 blocks. We have to be assured what we are getting. So you have to be careful when you are using these instruments. And I'm demonstrating to you because all of these instruments that we have, they are working perfectly. So if you submit to me and doesn't work, that's your own case. Are we together, class? Okay. So when I rotate this switch, then I have to check the display. Within this scale that I have chosen, I have two instruments. I have DC voltmeter and I have AC voltmeter. How you can differentiate? The AC voltmeter, it's the one which indicated by sinusoidal sign. And the DC voltmeter is the one which has been indicated by the straight line and 3 dots to indicate that this is a continuous or constant signal. So when you rotate, one of them should always be default. One measuring instrument, if you are using a scale of the 2 or more than 3 instruments, one of them should be always default according to the manufacturer. That's why you have to read the user manual of this multimeter before you use it. Are we together? So before I teach you, I have gone through the user manual of this multimeter. I don't know about you that possibly you saw them today, but you have seen in the other workshop. I don't know even if you bother yourself to go and dig it. Okay. So the default measuring instrument here is the DC voltmeter. So I have to use the selector button in order to change the instrument from the DC voltmeter into AC voltmeter. So this is the selector button according to this multimeter. So I press it. So when I press it, I will see a small text that written AC. You have to be, whenever you are using digital voltmeter and the digital AC voltmeter and digital DC voltmeter, you have to be extraordinarily careful. Extraordinary what? Extraordinary what? Why? Because you can use AC voltmeter to measure AC without destroying the AC voltmeter. But when you use DC voltmeter to measure AC, you are destroying that DC voltmeter and you are destroying the entire multimeter. I don't know if you have heard what I'm saying. Let me repeat. You have to be extraordinarily careful when you are using AC voltmeter and DC voltmeter, or when you are using AC ammeter and AC voltmeter, and AC and DC ammeter. Why? AC voltmeter, the goodness, it can measure both DC and AC without any problem. Okay? But DC voltmeter, once you use it to measure AC, regardless of the magnitude of AC, you are destroying the instrument, that measuring instrument, and you are destroying the entire digital multimeter. Are we together? Are we together? Yes. Okay. We used to say that prevention is better than what? Prevention is better than what? Cure. So I have told you, when I find you that you've done a mistake, you bear the cost. So keep on slumbering. Keep on what? But the slumbering you are doing right now, it will cost you soon. Okay, let us continue. So again, I have these positive leads and the red positive leads. So I want to use the AC voltmeter. So I have two choices, whether to connect this positive lead in this hole, or to connect the positive leads in this hole, or to connect the positive leads in this hole. So if you read the scale that have been written in this digital multimeter, then you see here we have a capacitance meter, here we have a voltmeter, here you have a ohmmeter, here you have frequency meter. So because I wanted to use, or we have to use AC voltmeter, I will connect this positive lead in this hole. Then next, I have a negative lead. So in this negative lead, I always have one hole that I have to connect. I cannot connect this black lead into this hole or this hole. This black leads, in case of the measuring instrument, we call it common. And that's why I told you that we have a common ground. And this is the common grounds in case of our measuring instrument. Then we connect it. But again, sometimes you might do, many students, they used to connect these probes without even taking care or be assured if it is connected or it's not connected. So in order, before you do any measurements, you have to be sure whether your digital multimeter is well connected, these leads or these probes are well connected with the digital multimeter or are not disconnected. So the alternative way, you have also to rotate this pointer or this rotary switch and to point it into the continuity tester to test what? The continuity between the positive leads and negative lead. So if that's the case, then I can select it. So you see this is the continuity tester, and then I have to short these two. So when you hear an audible sound, then you have already connected your positive lead and the negative leads to the digital multimeter. So from there, you may continue with the measurements. Are we together? For instance, if example, unfortunately that I was not careful. For example, that I did not connect this ready or positive leads, then you don't hear. So for instance, that if example that is loose, you cannot hear what? The audible sound. Okay? So the first thing, you have to be sure that you have connected, that's good. So then you come back to your AC voltimeter. Remember the default is DC voltimeter. So you have to press what? The selector. Now we have what? AC. We have what? AC. Eh? How do you know that it's AC voltimeter? The display. We write the abbreviations of alternating current, which is AC. Are we together? If you don't see that, don't try to measure AC. Okay, good. So, now, I have to measure the AC, and you can take a record. But these are my readings, not your readings. Okay? When you observe this power cable, stop. 60.77 what? Cows. Always you forget the unit. And that's the kind of the engineers that we have in our country. But you learned the concept called SCI when? Form 1. In topic of 40, measurements. So you just mention 60.77, then you forget the unit. Class, are we together? This is for the non-center tape D transformer. Then we are going to measure again the output root mean square voltage of the black wire and the other blue wire. Then what do you see? A? 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 Pardon? Again, say it loudly. 6.774. Okay. Then I told you that because this is the center tape D transformer, the output between this blue wire and the another blue wire, theoretically we have been told it is 12 volt. Let us measure if it is true. Right? And then see the theory. Then this is the measurement. What do you read? Speak loud. You like this stuff. Today you see them. Point to point. You are unhappy. For me, I'm happy to teach this stuff because I'm born to come and teach this stuff. I'm doing my purpose. And you're also supposed to say that you came also to learn this stuff. But you're unhappy, unfortunately. I don't know why. Can you ask your neighbor, are you happy? It is what? Eh? Okay, so I disconnect it and measure it. Did you record it? Eh? Is there any change? Some say yes, some say no. You cannot say yes while your mind is not here. Do you say, what now are you, what is your reading? Eh? 13.5. The same reading? No. But I didn't change anything. I'm trying to demonstrate to you something in a very simple language, but it's very practical more than you think. What reading do you read there? Is it the same? Okay, fine. So we are done with that one. In order for you to get the output maximum voltage of the step-down transformer, you know what you have to do? Simple calculation. Take what we have measured, you multiply by under root of 2. Is it difficulty for university student? No. So have you computed? you don't have a calculator. Why? Because this is not an exam. Okay. This is our step down. This is the breadboard. We are done with the step down transformer. You have to be careful with these wires. So the ground, the center tape the wire. If you don't need to use it, you can just connect it with this point where that you have to fix it a step down transformer. Okay. With this breadboard, simply the breadboard has been divided into three main parts. We have a power section, which is this one and this one. Also, the second part, it's a power area. And the third part is the IC base area. Are we together? Are we together? Yes. Should I repeat? Let me repeat. But there's a video that I've made of 1 hour and 30 minutes. I've been teaching my electrical students about the breadboards. It's all only 1 hour and 30 minutes about the breadboard. So you'll know in detail. So I don't have enough time to teach you what is hidden. Because within this breadboard, there is a hidden story. Okay? Yes, good. So I said we have three main parts of the breadboard. The first one is power section. But this, the power section, we have two. It's also divided into two parts. We have a positive power section and negative power section. And also you have a positive power section and negative power section. In a simple language, these two rails, we call them rails. Say rail. Say them rail. Do you know a rail? Do you know a rail? You just know railway. You don't know a rail. Huh? What the means of rail in Swahili? Rail, right? What does the rail has? What the structure of the rail? Actually, it's two structure. The long iron material and also the what? The holders, right? So this is the power rail. This also is the power rail. Then this is the circuit area. This is the circuit area. This is the IC base or integrated circuit base. Are we together? So it means that we are going to build our circuit. We have a permission to build our circuit only in the circuit area. Once we have our power, then we'll do something later. So I put the breadboards on the table. This is the working bench. The next components, according to the block diagram, we say that it is a rectifier unit. Right? Right? Yes. Okay, good. So for the rectifier unit, I'm going to build, I said you can build the rectifier unit by either using individual general purpose diode or by using the bridge rectifier IC. We have covered it in theory, right? So we are going to implement the bridge circuit by using the individual diode or by using the general purpose diode. In electronics, we have more than 10 types of diodes. For you, you learned one. Or maybe you learned it two, especially some of them in power electronics. Possibly you heard them, but I don't know how you have followed them. So in electronics, we have a general purpose diode and we have special purpose diode. So this is the general purpose. Okay? 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 This is the semiconductor device. So the diode, it has two terminals. The anode and the cathode. The physical appearance of the diode, it has two colors. Black color and also it has a white or we call it a gray color. So the gray color, the terminal which has a gray color, this one, gray color, is called the cathode. The terminal which does not have a gray color is called the anode. So how many diodes are we going to use? This is number one. So there's a different way that or different configuration that you can connect your components in the breadboard. But remember to use the circuit area to build your circuit. Don't try yourself to use the power sections to build your circuit because you can cause electric shock. Okay? Samuel is Samuel. Good. Okay. So then now you can check. So either I can just put these diodes in the different configuration. You can check your schematic circuit diagram. So I can connect the first diode here, and then connect the second one, so you can visualize. You can connect it here. So that is diode number 1. So it is diode number 1. Left hand side is anode, right hand side is cathode. Derek, good. Keep it up. Okay. Then I'm taking diode number 2. Diode number 2, also I have to connect it careful because the anode of the first diode should be connected with anode of the second diode. So I connect them in these holes. This breadboard, you can use a breadboard to build a circuit which contains more than even 30 components. But because you're a beginner, don't bother yourself about the use of the small section. Right? At this time, just try to use as well as you can. When you be learning about other parts, then you learn about how to budget the space of the breadboard. Are we together? Class, are we together? Yes. Good. Then I'm taking now the third diode. So remember that this is the common anode. This is the common. Where I have placed the finger, it's common what? Anode. Then I need also to have a common cathode. So a common cathode. Okay, you have to make sure that there's no any physical touch or contact between one diode with another diode. Because if there's a physical touch or physical contact, you can destroy the diode. Are we together? Are we together? Then I'm taking the first diode. So the first diode should be connected in common with the third diode, so the common cathode. So here we have common cathode. So this is the implementation of our bridge rectifier. Regardless, you can number this one diode 1, you can number this one diode 1, diode 2, diode 3, diode 4, whatever that you can number. But remember that this is the common anode and this is the common cathode. Are we together? Next, you have to turn off your power. You have to be careful. We used in our design a step-down transformer of 12 volt. Right? So I'm going to take these two wires that giving me almost 12 volt. Okay? Okay? I say that you have to connect them careful. So, in order to budget the space, okay, so I take one wire of the step-down transformer and connect it here. And then I have to take the second wire and connect it in between of the other step-down transformer. So I can connect it here. You have to be careful. Your step-down transformer should be always stationary. You should not touch, should not shake the bench. So from there, now I have connected the output of the transformer, or output alternating voltage of the transformer, to the what? To the what? Bridge rectifier. So in breadboard, we used to do measurements by using jumpers. Say jumpers. In electronics, we have 3 types of jumpers. We have male to male jumper, we have male to female jumper, we have female to female jumper. Okay? Okay? So I'll be using these 2 jumpers for this case to do the measurements. So intentions of these 2 jumpers is just to do the measurement. So remember, where do we have a positive? Where is the positive terminal? The common cathode is a positive, or the common anode is a positive? Students, I have students here that I have taught them more than 5 to 6 workshops. But unfortunately, they don't remember, they don't answer those simple questions. In bridge rectifier, tell me the point where we have a positive. Is it a common cathode or common anode? Eh? Thank you. But you are wrong. I'm very sorry that you are wrong. Okay, refer your schematic circuit diagram. Refer. Refer your schematic circuit diagrams quickly. I say refer, every student in this class, refer your schematic circuit diagram and tell me that. Because in bridge rectifier, we have input 1, input 2. We have output 1, we have output 2. So for the output, we have a positive terminal and a negative terminal. My question is, where do we have a positive terminal? You told me that common anode. Now you changed it again. Huh? You know why did you say that it's anode? Because you have claimed it that always if you have been given a diode, the anode is positive, the cathode is what? While I'm not talking about individual diodes, I'm talking about bridge circuit. Okay, but because you are Tanzanians always, you are perfect. So, the positive terminal is where? Common cathode. The negative terminal is where? First of all, that transform your knowledge. We taught you that the anode of the diode, individual diode, is what? Positive. Or should be connected to the positive supply. It's not positive. Anode is anode, anode is not positive. Cathode is cathode, cathode is not negative. Are we together? Are we together? Okay, well. So if that's the case, now we are going for the next part. We want to measure the output of the bridge rectifier unit. So I have this yellow one. This is connected to the common what? If you do remember, I say that in this bridge circuit, this is what? Common anode. And this is what? So this one will be what? Negative or positive? Positive. And this one will be negative or positive? Okay. So if it's, and you have to be careful because when I've been preparing this experiment, I remember that I did a mistake and I burnt out a diode. So for you, you could say that, just build a bridge rectifier, it's simple. Good. So that's why that even you don't care, that you can build it within a fraction of a second. So you can turn on your power source. So we said, or we learned that theoretically, the output of rectifier unit is the C component. Right? But when we did the simulation, then we experienced something which is unexpected in theory. We experienced that the output signal of the rectifier contained the C signal and the C code. So if that's the case now, let us start with the C. So rotate your rotary switch from the off or from any point to point into the C voltmeter. So we are going to do measurements. So this is positive lead, this is negative lead. So I connect it here and then I connect it in this yellow. So, what the measurement? 7.20? Students, read what you see there. Okay, it's varying, Okay, so if it's varying, let me show you something. So what do you see there? Record it. That is what? DC output of the bridge rectifier or AC output? Good. Then we are going to the next measurement. Have you finished the record? No. Tell your neighbor electronics is beautiful. Tell again, electronics is beautiful. Yes. Do you have a question? There's somebody who said, sir. If you have a question, just raise up your hand. Okay, up to that point, is there any question? Yes, welcome. Go straight forward to the question. Okay, Johanna is asking a question. We have a center tapped step-down transformer. And then he said that, according to what he understands, the center tapped transformer, it has positive and negative terminal. Is it true? The center tapped step-down transformer, it has positive and negative. Is it true? So your question is? Okay, so the questions of Joanna, he asked us, this measured value, which is the output of the bridge rectifier, should we multiply by 2 or we leave as it is? The answer is what? You don't know even yourself. Did you hear Joanna's question? Who can answer? The class is quiet. Who can answer? Kevin. Should I go out also like you? Class. Did you hear Joanna's question? Listen, I told you this. In case of the DC component, we don't have root mean square voltage or root mean square current. DC voltmeter, I taught you in the class, in the theoretical class, always measure the maximum DC voltage. A DC ammeter always measure the maximum current, DC current. So the issue of root mean square voltage, peak to peak voltage, maximum voltage, and minimum or whatever average voltage is all about for alternating signal. Are we together? Are we together? Is it clear? Yes. So we used the DC voltmeter to do measurement. So the reading we have, there is no need to multiply with under root of 2. You know the challenge you have when you come for practical. you were expecting to see the new miracles. So you leave the theory behind. Eva, is your friend okay? Your neighbor, is it okay? Is he okay? Check the way that he sat. Okay, so we are going for the next measurement. Let me continue, because you told me that, sir, continue, keep it up. Right? Let us continue. Or should I not continue? Eh? Okay. So we are going for the next measurement. We told you that theoretically, a diode conveyed this AC into DC. But practically, you could have seen, even that DC, it was not steered DC. It was alternating DC. If you have been analyzing, you saw the readings vary. Okay. So if that's the case, we told you that practically, the bridge rectifier can convert the AC into DC. But the outputs of the bridge rectifier, we told you that we have DC component and AC what? Eh? So now we are going to use AC voltmeter to do the measurement, to measure the AC component. Okay? So I have to use the selector button to change the instrument from DC voltmeter into AC. Then I'm going to measure the output of 40, the outputs of the bridge rectifier circuit. So what do you see there? Okay, record. Ready? Nora, ready? Ready? Okay. So we are done with the measurement of 40 of bridge rectifier. Right? Right, class? Right? I know that you have built the bridge rectifier, the linear power supply on the breadboard, but I know you have never done a measurement. 20 to 20. Is it true or is not it true? Okay, fine. Let us continue. The next block? Okay, refer. Maybe you forgot. For me, I didn't forget. The next block? A? Filter unit. Are you ready for the filter unit? Okay, so you are going for the filter. How many components do you have for the filter unit? One. Right? What's the name of that component? A? Electrolytic capacitor. Theoretically, we calculated and then we said our choice of the standard capacitor, or what the capacitance of the standard capacitor? 5,000 microfarad. When I've been teaching about theory, I did not teach you anything, or I have just mentioned another important parameter that's called the voltage. Capacitors are manufactured on focusing with the two parameters, which is capacitance and voltage. It's just like a resistor I taught you in simulation. Resistors are built with the great focus of the two parameters, resistance and power. So another thing which it has been hidden long time in your mind is about the voltage that the capacitor, the voltage of the charge that capacitor can store. So we discussed that we need a capacitance of 45,000 microfarad. So the issue is not electric capacitor. It's not any electric capacitor of 5,000 microfarad that can filter the AC components and remain with the DC component. Another thing that you have to know also, the input voltage that you are going to feed into the filter unit. So the input voltage always should be less than the rated voltage of the capacitor. Did you understand what I said? Capacitors, electric capacitors, and even ceramic capacitors are manufactured based on the two parameters. Say capacitance, say capacitance, and voltage. So if you have a capacitor of capacitance 5,000 microfarad, but its input voltage, or it can store the charges of the 16 volt. When you connect it with our system, that capacitor is going to burn out. And it is simple because I have mine, so we can test. Because for you, I think that it's better to prove, to see, rather than to hear. Okay? So, that's why we've been doing calculations. That's why we've been doing theoretical. That's why we've been analysis. That we've been doing design. And then we went for the simulation. So when you come for the practical, you can find a capacitor of 5,000 microfarad. But if the voltage, which that capacitor, which is the rated voltage, is less than the input voltage of your linear power supply, you are going to burn out the capacitor. Are we together? Are we together? So instead of 5,000 microfarad, we are going to use a capacitor of 1,000 microfarad. But the rated voltage is 50 volt. Why? Because if you do remember, during our calculation, we say that if we have a root mean square voltage, students, it's not the time for the computer. If you have a root mean square voltage of 12 volt, if you convert it into maximum voltage, we got 16.97 volt, right? Then in bridge, we say that when the bridge conducted, the two diodes conducted, then we have a potential drop of 1.4 volt, right? So in theoretical, we knew that this it means the maximum output voltage of the bridge rectifier should always be around 15.30. So if you have a capacitor that can that is rated, Kankesha, that is rated with 50 volt, I will be in safe zone. But if I be using the capacitor of 1,000 microfarad or 5,000 microfarad, but the rated voltage is 16 volt, I'm in danger. But I know that because you like it to see, I will show you how you can burn that capacitor. I don't have it. I will have it within a short time. Okay? Are we together? Electric capacitor has polarity. This is the positive terminal. This is the negative terminal. The negative terminal is written as negative. If you do mistake, and then you reverse the polarity of this capacitor, you are going to burn it. Im, are you there? Okay, fine. So this is the negative what? A. So it has been written what? Negative. Zoom this one. So this is negative 10. The two parameters that I've been teaching you for this electric capacitor are this. What the capacitance? A. What the capacitance? 1,000 microfarad. What the voltage? Good. So we are going to connect our capacitor with the output of the bridge rectifier, which is common what? Common cathode. Then, from there, I have to establish a common ground. So I have to take another jumper, because now I need a common ground, because I have a DC component. So the common ground is always common anode for this bridge rectifier. So this is the common ground. So I have used the power rail, and this the red one, this wire. I'm establishing the common ground because the negative terminal of the capacitor should be connected with the common ground. Are we together? Is it not clear? Okay, thank you. Let me repeat because I love you. I say this electrolytic capacity has polarity. And the way that you can identify the polarity by using or by reading the label, which manufacturer has made, this is the negative and this is the positive. But another way that you can identify the polarity of the capacitor or electrolytic capacitor by using or by examining the length of the leads. The positive lead is always positive. The longer lead is always positive. And the shorter is always negative. But sometimes if you are using a capacitor, electric capacitor like this one, which its pins have been shortened, it is difficult to use or to examine the terminals and determine which is positive and which is negative, because the length of the terminals is the same. Okay? Okay? So go to the schematic circuit diagram. The positive terminal of the electrolytic capacitor is connected to the common what? Common what? The negative terminal is connected to the common what? Why? Because common anode is common ground. Okay? So I said, I have to connect it there because this is the circuit area. I have to establish the common ground. So I took a jumper and connected the common anode with the common grounds in the power section of the breadboard. Are we together? So that's the exercise that now I'm doing. So it means the first rail is common ground. Right? Look there. Then I take the electrolytic capacitor, I connect the positive terminal with the what? With the common what? Common ground. Positive terminal of the capacitor should be connected to the common ground. My God. Common what? Common cathode. So I have connected the common cathode of the bridge rectifier and the positive terminal of the what? Of the capacitor. Then I have to connect the negative terminal of the capacitor with the what? Common what? Common what? Common ground. So remember, when your power source is turned off, okay, so I'm done with the connection. So now we have a bridge, we have what? A filter unit. We have a step-down transformer, we have a bridge rectifier, we have a filter. I'm going to turn on the power source. Okay? Okay. So I've turned on. So if I have turned on, now we are going to measure the output voltage of the filter unit. Right? Okay. So how can I measure it? The measurements has to change. I have to take one jumper and connect the common ground, and also I have to take another jumper and connect it to the positive terminal of the OT of the positive terminal of the capacitor. So I have my jumpers now. Positive terminal, so this is the jumper for the positive terminal of the filter unit. And also this is the negative terminal. Remember that another thing which you have to make sure that you check the connectivity of your components. Because sometimes you can be doing measurements while another component is not well plugged within the breadboard. Okay? Well, so then we are going to measure the output voltage. So what the output of the filter, which we expecting? DC or AC? What its nature? So we have to turn our rotary switch to the DC voltmeter. Then now I'm doing the measurements. So while we are zooming, you can see that the output of the filter unit is what? Pardon? $17.20, but it's changing. For we who love this business, it's what? Even if it is changing with 0.01 decimal point, it's very important in engineering. Then let me hold the one value and record it, because you know you are my beloved student. I love you by default. And my love always is default to you. But for you, your love is always special. Record it. That the output voltage of 40. So if you do remember during simulation, when we have implemented the bridge rectifier unit and the filter unit. Then we went back to measure the output of the bridge rectifier unit. Then the readings were not the same. Why? Because we have connected the diode with the bridge rectifier in parallel. So it means that the DC voltmeter that measure the electric parameter is connected across the bridge rectifier. At the same time, it's connected across the filter unit. Are we together? Are we together? Then. I have to repeat. I said, if you do remember in what you've done in simulation, we implemented the bridge rectifier itself. We measured the output parameter. If you do remember, we measured the AC voltage, we measured the DC voltage, we measured the AC current, we measured the DC current. If you do remember. For me, I remember. We did that with you. Okay? Then we build the filter unit. Once we finish to build the filter unity, when we measure the output of the bridge rectifier, while the filter unity is there, we don't get the same parameters as when we measure the output of the bridge rectifier when it was itself. Then I ask you a question, why? Right? And this is the answer. Because we have connected the capacitor in parallel with the common cathode of the bridge rectifier. So if you connect, remember this DC, either DC or AC voltmeter should be connected across or in parallel. So when you measure the output of the bridge rectifier, when you have a filter unit, you are measuring either the output of the rectifier or the output of the filter. But the output of the rectifier, it will change because now the filter is the one that's dominating. Okay, you'll understand it slowly, like what the Kankesha is doing. Kankesha is Kankesha. But we said also, the filter unit will draw the AC components or the ripples. Do you remember? Eh? So the AC components will be alternating. So let us use the AC voltmeter to measure what has been stored within the capacitor. Okay? So I have to switch my measuring instrument from AC to DC. So from DC to AC. So now we are measuring the amount of voltage of the ripples. But remember, when you use AC voltmeter, it gives us the root mean square. When you're using DC voltmeter, it gives us the maximum. Okay? Well, so you're going to measure what has been stored within the capacitor. So what do you see? So read the maximum reading that you see there. Maximum is? You cannot see because your mind is not there. 5. Uh-huh. 1. Eh? Pardon? That is AC, so AC is alternating. And that's why it is alternating. Hey! So you are experiencing to draw the sinusoidal, and then you think that the measuring instrument will not give you the fact. What the reading? So give us the maximum root mean square voltage. 420? 5. Or you approximated 5. 5.0. 5.2. Now 5.2. So you could sense and you could see what is going on in the world of practical electronics. So we used to tell you that theory and simulations are simple. This is just a small circuit, but you have already been confused again. But you have a plan to one day to build or to design your own robot. That's your vision, right? And I want to tell you that you can, but change your mindset. Okay? You have a plan one day to design your mobile phone. It's fine, we are waiting. Because 10 years ahead, the mobile phones that we have will be throwing them because they will not be in use. They will come new and modern fashioned mobile phone. Okay, so so you can read. Can you note any of that reading? So another question as the engineer, what's going on there? Why is going to 9? Why is going to that? That's what you have to bother yourself. You have to think. You have to go back to the theory. Okay, you say that that's not our business. Good, fine. So I think that so have you recorded that? I told you that this is a practical class. It's all about the measurement, numbers, and we have tables. So that's what because I used to tell you in theory, I want to demonstrate to you. You don't record. You just say 9, 5, 9, 5. And then what did you record? Record what you have seen. I know, you'll check your neighbor. You just amplify your neighbor's reading. And then you say, so my neighbor has written 5.2. So let me write 5.21 to be different. Because this is practical. Are we together? So you saw the ripples. You saw the what? The C or the unregulated DC signal from the filter. Good. So here we go. The next block, we are done with filter. We move on. The next block, voltage regulator. Wonderful. So this is the voltage regulator. Look. Happiness, God bless. Look here, please. This is the voltage regulator. This pin or this hole is important to fix something we call it in electronics heat sink. One of the part, I don't know if you have asked yourself about why your personal computer has the built-in fan. I don't know if you have bothered yourself, ask yourself that question. Okay? Or for instance, if you're using your computer, you have a song that or a move going on through VLC, you are online, you are using Google, at the same times that maybe you are writing an email or you are browsing, maybe you are doing this and that. If you give your machine or your laptop multiple tasks, is going to overheat. Okay? Okay? So I want to tell you that what you have been seeing in the finished products, such as your mobile phone. For example, if you have a long talk of maybe 3 hours or 1 hour or 2 hours, you hear that your mobile phone is hot. So the concept of heating in electronics, whenever we are building intelligent system, we also encounter another challenge of heat. So heat is not a good characteristic for electronic system. Eliakim and Emmanuel, something is going on there. So this is important to figure out the heating sink. Do you know the meaning of the word sink? It means the function of the heat sink is to absorb the amount of heat that will be dissipated because there's a flow of electricity that will be passing through this integrated circuit. So there is a heat dispersion where the electric energy is converted into heating energy. So this, I see it has been made to sustain the particular amount of the temperature. If the temperature exceeds its capacity, it's going to burn out. One of the sensitive devices, you can burn out a diode, you can burn out a capacitor, you can burn out a voltage regulator. And sometimes the voltage regulator, when you burn it out, it does not show any sign. For the capacitor, it's fine. Students there, they are drawing the schematic circuit diagram of linear power supply. So if you put in this way, then the first pin from right is input. The middle pin, according to the data sheet of the manufacturer of LOM 7805, the middle pin is ground. Then this pin on your side, which is left-hand side pin for your side, is output pin. Zuena Sunzu, you are not in this class at all. And thank you for being out of this class. So you may locate this voltage regulator on the breadboard in this way, or you may locate in this way. But you have to remember, if you locate in this part, you have to know where the input is on the right hand side. This is the common ground. This is what? The output. Are we together? Are we together? So now let me place the voltage regulator into the breadboard. The next step, I need also to connect with ceramic capacitors. Okay? Also, we say that the ceramic capacitor is 0.1 microfarad and also 0.3 microfarad, or 100 nanofarad. And also we have, remember that the ceramic capacitor does not have polarities. So then we connect it at the output terminal. And remember that the ceramic capacitor, one terminal should be connected to the input of the voltage regulator, and the other one should be connected to the ground. So the next process, I take one jumper and connect the ground of voltage regulator to the common ground. So here the common ground. Then the next step, I have to connect the input pin of the voltage regulator with the output of the filter unit. The output of the filter unit. Okay, so we have finished our connection. The next process now, we are going to measure the output voltage of what? Of the regulator unit. So how are we going to measure? We have to measure the potential drop between the output pin and what? And the common ground. Don't call it ground, common ground. Check your neighbor. What is he or she is doing? Once you see, just smile and then accelerate him. So now we are going for the measurement. I'll tell your neighbor we're going for the measurement. Eliakimu and Emmanuel, keep it up. Keep drawing that schematic. Okay, so these are the leads. So we are going to measure. Remember that we say the function, a voltage regulator has so many functions. But one of them is actual to regulate unregulated input signal. To provide a regulated signal. Are we together? Are we together? So we expect it, because the voltage regulator that we are using, it is LM7805. According to the manufacturer, it can give us a typical value of 5 volts. But also it can give us a minimum value of 4.98 volts. And according to the manufacturer data sheet of the manufacturer's data sheet, also it can give us a voltage of 5.2 volts. That's the maximum. Okay? Okay? Now I'm speaking the technical language more than you think. So we have our DC voltmeter. Then we are going to measure what we have at the output. Which for you, if I could ask you to do measurement, you could just go straight forward and check what the output. But I turned off the power. So for instance, if you measure, because let me share with you some challenges, that you are measuring the output voltage, but it's not there. The issue is not your circuit. You turned on the source of 40, your power. Do you see any reading there? You might say that the output voltage is 0.012 volt. In Bongo land, we can say that. And the voltage regulator is not 40. Why? The output voltage is what? 0. So let me turn the source of power. When I turn the source of power, then we measure the output voltage. What is it? Record. Okay. Again, we have the 50 block, which you say the load. You remember that? Eh? Yes. So the load, for the simple demonstrations, because I said that the linear power supply that you are going to design today, you will be using in any kind of the design that you'll do in electronics or in telecommunication engineering. So this is the resistor. It's a low power resistor. I don't want to tell you or to mention its resistance, but I can determine its resistance theoretically by using the color code. And also, I can determine its resistance by using the ohmmeter. How? Look there. You are looking nothing there. So we are going to connect, according to our schematic, we have to connect one terminal of the light emitting diode. We are going to connect it in. But before that, remember that now we have our output DC voltage, which is 5 volts. If you do remember, go to the schematic circuit diagram. If you do remember, when we've been drawing the schematic, the common ground, I also drew something which you call the connectors. Do you remember? So now the breadboards, I have a rail, which is common ground. That is what is representing the connectors that I taught you in theory. So before you go for the load, you should also have your common output power, which actually will draw what you can take your output current from your linear power supply. You can draw your output power, or you can draw the output voltage from your linear power supply. If you do remember that when I've been teaching you about schematic circuit diagram, we had a block of power supply unity here. And then this block is supplying power. Right? Right? So to supply power, it means that the output of this power supply unit should be connected or should be common in order to supply power to the different sources. Okay, let us continue. So, you have to take one jumper and connect the output terminal of the voltage regulator with the common power rail. Now shown. Now shown. Keep it up. So now, in the power rails, I have a common ground. I have also this wire, this red wire, connected or established the common rail or common grounds in the power rail. Right? And this wire, this one, the one that I hold right now, it have connected the output of the power supply to the common power source. So it means that all these rails or the holes of the breadboard represent different connectors. If you wanted to implement our circuit in the variables of breadboard, we are going to use either connectors or T-blocks in order to draw the output of the linear power supply and establish the power bank. So if we need an amount of power, or we need power to take power into the input unit, there's no need for you to come and actually to try to put the put the jumper around the output pin of the voltage regulator. So for instance, the breadboard city has 50 pins. So now I have connected the common positive and the positive rails by just using one jumper. Then I have 49 holes that can supply power to anywhere. Okay? I took one jumper and then connected the common ground in the circuit area with the common ground in the power section. So it means that I used only one hole of the common ground rail. So I have 49 unused rails. So in case I need ground to any part of the sections of my design. I just take a jumper and connect it within those 49 holes which are not used. Class, are we together? Can I have a piece of chalk? Can I have a piece of chalk? Come basi I have a piece of chalk naangalia. Stop basi mzee. We need our power indicator. Remember, you have to turn off. Hawa, 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 hawa. Hawa, 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 hawa. So remember, this is the light emitting diode. The goodness, when it receives a minimum amount of electric current, it gives you power. It gives you light. That's the goodness. So whenever you're being given a light emitting diode, for you, you might see that this is normal. Light emitting diode, this is normal. But this is R, A, E, O, U in electronics. And this is the simplest semiconductor device. So whenever you're being given, the first thing you have to check it, whether it's working or it's not working. And simple. Don't connect this with multimeter to measure, or don't connect this with the battery because you're going to burn it out. Okay, Nation say that, sir, those stuff are simple. Why are you spending much time? So you have to connect one terminal of the resistor with the output terminal of the voltage regulator. The light emitting diodes also have polarity. It has cathode and the anode. But for the light emitting diode, the cathode and the anode can be notated as positive and negative. So the anode is the longer pin. Remember that this one is not converting AC to DC. This is the special purpose diode. Theoretically, diode convert what? DC to, and this one converting AC to DC, eh? Okay, good. Keep it up. So, the longer terminal is positive. The shorter terminal is negative. In case you find a light emitting diode where its terminals are equal, you have to try whether to connect in reverse or in forward. Are we together? Are we together? So for this case, this is the longer. So this is positive, and this is negative. So the positive terminal, you have to connect it to another terminal of resistor. And the negative terminal, you have to connect it with the common ground. Good. Remember that this is the power indicator. Power. So I have connected one terminal of the light emitting diode with the one terminal of the resistor. Now I'm going to connect one terminal of, or the negative terminal of the light emitting diode with the common ground. So I'm going to turn on the power. So you don't see the LED lighting. That is good. For me, I'm happy. I don't know for you. I had DC voltmeter. I want to measure the output. Okay, there's a disconnection of the step-down transformer with the power cable. Thank you, Ruben. Okay, for instance, for this case, you see that the output voltage of your voltage regulator, what the reading? 5 volt. But the light emitting diode is not turning, right? So if it's not turning on, that is fine. So the issue might be the light emitting diode. Then this light emitting diode also is not turning on. This does not have a problem. Man, okay, so let us continue. When you've been implementing the 50 block, for you are continuing on another side. Okay, be back. You are continuing on your mobile phone. Be back. When we've been implementing the 50 block, we have experienced the challenge that the power supply, the linear power supply was working, but the light emitting diode was not turning on. So, might be, there are the two possibilities. Maybe the resistance, the limiting current, Gertrude, the limiting current resistor has a high resistance, more than the minimum or the maximum resistance that is required. Or another possibility, maybe the light emitting diode that you are using, it is burnt off. Because light emitting diode, these are the special purpose diodes or semiconductor device which are very sensitive to the amount of current. When they have been built by the manufacturer, there is a maximum current that the light emitting diode can withstand. So when it exceeds, it burns out. Did you understand? The cause of the challenge that we have experienced might be either one of the following cause. The first one, maybe the resistance of the resistor that you are using to limit the current is higher. So it's limiting all amount of the current in such a way that the amount of current reaches the light emitting diode is less than the minimum required current to turn on the light emitting diode. That's the first possibility, right? Right? The second possibility, maybe the light emitting diode that you are using has burnt out. Okay? So how can you be sure with the limiting current resistor that you are using and the light emitting diode that you are using in your design? The simplest way, I told you that whenever you're being given electronics components or electronics materials that you have to use in a practical, it's better to check every component before you use it. Right? Right? Because when you build it a circuit of 5 to 6 to 7 or maybe 20 electronics components and you test it does not work, you don't know where the problem is. Are we together? Okay. So alternatively, you can have a battery like this one which is 9 volt, and it's a holder. Then you can test your limiting current resistor and light emitting diode separate first to check whether they are working or they are not. Right? This is the resistor of 200 ohm. I can tell you this one because I measured it. So you just connect a resistor and then connect to one terminal of the battery, which is positive, and then you connect your light emitting diode. I think that I have asked the working light emitting diode. So you connect the negative terminal from the battery. You give the diode the constant DC source. So now you see that the light emitting diode is lighting. Then we want to check the resistor that we've been using to check if it has a problem or the problem is light emitting diode. So if you do your connection, you see that the problem is not resistor. The problem is not what? Resistor. Okay, so you see that this is 1K, 1 kilo ohms or 0.5 ohm, kilo ohm, which is called 580 ohm. So it's on. So now, this is our limiting current resistor. Let us build it, the 50 block. So we connect it. You can even connect it the common power source. It's not necessary to connect it nearby the output terminal of the voltage regulator. Next, then I connect the light emitting diode. So when you connect the light emitting diode, then you connect the output or you connect the common ground with the negative terminal of the light emitting diode. Okay. So now we have our 50 block. Our 50 block, we say that we take a simple load, that is RAOO, or we call them SVOL, which consists actually what is the limiting current resistor and light emitting diode. So when you have this configuration, remember, you can measure the potential drop across a resistor, and you can measure the potential drop across the light emitting diode, and you can measure the potential drops across the output. So remember that we have a common ground. So we have our common power source or common positive source. So for instance, if I have a DC voltmeter and do the measurements, so this is what I measure at the output of our linear power supply. Now it is what? Zuena, now it is what? Zuena was not there. 5.20? Is it the same? No. Then let us measure the output voltage across, or the potential drop across what? Across resistor. Because we have two components there that consisting what? Consisting a load, a resistor and light emitting what? Diode. Okay, so the potential drop across resistor that we've used is this one. What is it? 2.21. Then let us the potential drop across the light emitting diode, because we have two components which are consist the load part. So this the potential drop across the light emitting diode. What is it? 2.60? 3.5 or 3 or what? 2.64? 2. Are we together? If there are any questions, please ask it. So remember, the light emitting diode is actually its power indicator. And remember that the output voltage might not be 5 volt, might not be even 4 volt. If the output voltage is 3 volts, it's enough to turn on the light emitting diode. Do you understand? So in case of any business that you are doing, whether on the breadboards or variables or breadboard, the multimeter is your best friend. Because it's not just you say, because the light emitting diode is turning on, so the output voltage is 5 volt. It's not true. Even the output voltage is 3 volt. The light emitting diode can turn on. If the output voltage is 60 volt, the light emitting diode can turn on. Are we together? Any questions about what you have been discussing? Raise up your hand if you have a question. We did the part of the measurements. We have done a lot of measurements. The matter of calculations is yourself to remember what you have learned in the previous concepts. And then you know the issue. Just the simple formula is multiplication. Tell me, when you've been learning theories and simulations, is there any measurements that I did not illustrate in this practical? No. About current. Yes, the topic of current is another topic. So I didn't discuss anything about current. That's another workshop. Okay? Any questions about what you have learned? Class, I'm giving you another chance. Ask me any technical question about what you have learned and what you have covered today. You're welcome. Pardon? I've explained I've explained what happened. I have mentioned two causes, or two reasons, or two causes of the situation that happened when we connected the load and it was not turning on. Did you make a follow-up? Yes, it was two possibilities of what happened. So which one is exactly for our case? For our case, the challenge, it was the light emitting diode. This is another one. I went and take the new one. Yeah. But another thing, sometimes I say, it might be the resistance of the resistor that you're using. Okay? Yeah. So if you touch the voltage regulator at this time, it's not too hot. But wait, in the next semester or even in a short moment, you will not be able to touch this voltage regulator because it is going to liberate or to generate or to give out large amount of heat more than you think, which you call the heat dissipated. Are we together? So if everything is clear, thank you very much for making a follow-up. Now it's a time for every student and everybody who is watching me to take all the resources that we've been using and to implement and build what you've been doing. For me, I thank God because I had a thirsty to show you what I showed you for the long time, but I thank God that today it became real. So did you understand? Okay, so let me congratulate you. I always appreciate you. I always appreciate online and physical students. So let us congratulate you because from 1st February to today, nobody who has congratulated you. They are always telling you that you are slumbering, you are not beautiful, you are not handsome. That's what you have been told outside there, right? You don't know anything. So let us now. 1, 2, 3. We like that in practical because actually it gives us a rest after a hard work. Thank you very much. Join me in the next workshop. Bye-bye.